Yeah, let's use big numbers. I'm just gonna use this again. ZZ.H. What else do I need? Compare this. Assert IO stream, yeah, I suppose. Hey, accelerator. I think I made progress. I'm starting to think that I can actually prove it now. But, well. Going to test a few things. It's, what types shall I use for big numbers? I think they're just number, I think. Just open both of them so I can see. That's the thing that you want to use there. Next. So that's my big number. Gotta do a test like in. How do you initialize a thing like this? Like that, I mean. Does this work is the question. This is the hello world of the big numbers. Yeah, and then I need to compile it, which of course I also forgot. Oh wait, I have maybe a makefile here. Yeah, might as well add that. Got this file now. We have lift off. Now these are infinitely big numbers. Well, yeah, the infinite, as big as my memory can hold. Don't have to worry about any overflow. Okay, wait, no, good. Right, so now what I want is yeah, I'm really going to skip all the even numbers. It's just not a thing. So I want to start with running over numbers. Oh wait, but start at 1 or no? Why not? And then n is less than can't do too much. I mean, does this compile? I'm just comparing a number with an integer here, so it's kind of, I don't know if it compiles. It compiles, and it works, no problem whatsoever. Right, then we want to print I want to find out what is the form of this number. Where form is so n equals maybe I should not have used n. Maybe I should have used k after all. Okay, I'm going to use k. Like I said before, I think about this while I lay in bed, trying to fall asleep. Well, not really trying, I guess. And then I'm using n. So this is the form 6n plus r. Well, then obviously r equals 0, 1, 2, 3, 4, or 5. And that for, let's say, n greater or equal 0, that defines absolutely every possible non-negative integer. But we only work with odd numbers, so if this is an odd number, then, well, because 6n is even, then r must be odd. So we only have to look at the 2, 3, or 5. And I think that's what I'm going to return as well. So we're now like k is even. Actually, I think I had a thing for that for is even or something. Is odd. Shamelessly copying from myself. Okay, so now it must be of the form 1, 3, or 5. And how do we find out? Well, modulo 6, right? That's strange. I copied it from the other one, other file. Oh, there's an unsigned long here. Yeah, I don't have another. I'm afraid we'll have to look up the documentation of NTLZZ then. Yeah, we have a percentage here. I can do that. I can pass it along and then it returns along. That should work. I don't know. I'll just use percentage. Oh wait, is odd. I need the percentage I need. Okay, and then this must be long, or but who cares? And then this one. I can do percentage too, but it's not something that's slightly faster. Oh, that's awesome. Removes factors 2 from x. And we have an is odd. That's what I wanted. I guess this is in NTL. Yeah, not passing odd numbers here. So that works. 135, 135, 135. Okay, then we have to do a step. Let's just return a number from a function that is called step, which takes a number. And now we do one Collatz step, as in it must be odd again. And then therefore I can do, well, I have a number result. Let's begin with setting result equal to k, 3 times k plus 1. And then we do the thing that I just found. It was called make odd. Returns the number of 2's removed. Okay, I don't care about that. So we can just do make odd on result. Okay, now my claim is that, I deduced that the forms 1 and 3 very quickly become 5 unless you end up with 1. So what I'm going to do is reprint it. Wait, I mean, reprint the number, so I'm just printing k. Every time I print k, I also want to print a form. Let's print that between form just being modulo 6 value, whatever, but well. So I print k, and then between parentheses what the modulo 6 is. And then I do while. Well, actually, it's just a big starting number. Let's KL, no, let's make K. K is function of L. I'm printing L, the form of L. Well, no, we can print K. Let's make a copy and then say while the form of L. It's starting to dislike that, so let's use braces. While the form of L is unequal 5. L becomes step L, so you just find the next one, and then of course you print it. Print L, or arrow L. Yeah, so I printed K, and then if the form of that K is unequal 5, then we do one step and then we print L. And then I want again immediately know what the form is also of L. And we continue that until the form becomes 5. Maybe I should replace form with mod 6. Probably slightly better in this case. Yeah, so substitute form with mod 6. My claim is therefore that if the mod 6 is not 5, which means that it is either 1 or 3, then this loop is always super small. Super small. I'm just not, I mean, I reasoned that mathematics, but now I'll just try it out hard brute force basically. How does that work? Wait. Turn make odd, just like that. And it's probably in NTL. Yeah, and then of course it becomes 1. Haha. Oh, we have a trick. We have a special trick for comparing with S1. I saw that there is an is1 here somewhere. It's probably faster. Oh well, find that back. No, why did I even remember that? I should probably just start at the top. Yeah, is1. And the wrong button. Okay, where was I? NTL is 1L. 2 rather not, right? Of course, yeah. So the modulo 6 of 1 is 1, not 5. But if it is really 1, then we won't stop as well. Not working. I just forgot to print a new line. Oh, this is longer than I had expected, I must say. Or maybe, yeah, that was a different reasoning, I guess. It's a reasonable short, but... Okay, so you can deduce that 1 goes to 1 or to 5. So you'll never see 1 going to 3. And we stop at 5, so each of these sequences ends with 5, and before that you only get to see ones. For example, 1, 1, 5. Or if we pick a longer one, 1, 1, 1, 5. 1, 1, 1, 5. But there must be numbers that are 3, of course. And I have no idea why I'm not seeing that. For example, 9 would be 3. 9. Oh, 9 is 3. Yeah, of course. You see the 3 only here. Because a 3 always goes to a 1 or a 5. Always. Then you can prove that. And a 1 goes either to a 1 or a 5. And we end at the 5. So I'm not saying anything about 5 yet. If that is true, and well, it's simple, easy to prove that you can never get a 3 after doing one step. So it's always going to either 1 or 5. And therefore, if you prove the Collatz conjecture for the 5s, then you have proved the whole Collatz conjecture. Because then it will also hold for the 3. Because the 3 becomes a 1 and the 1 becomes a 5. And in the 5 you say you have proved, right? But we still have the problem here that apparently it's possible to have multiple 1s on a row. And then you can ask yourself, hey, but then don't I have an infinite number of 1s on a row? And then the reasoning here is that no, because you can never get a value that is larger. So if you go from 1 to 1, it gets smaller. So either it becomes a 5 or it ends in 1. I think I should print a 1 as well. If we reach 1, we should print it. I should print it here already. I should print 1. Wait, why am I not seeing any 1s then? Yeah, that's not the one that I wanted. Yeah, it's printing 1 1 here. Oh, and here too. And here too. Okay, it just prints the 1 as well. Yeah, I don't know what the reasoning was. I don't see it grow indeed. So if you go from a 1 to a 1, it gets smaller. Is that always the case, is the question. Let's just do a brute force. Okay, so we already proved it for 3. I mean, we are already skipping even numbers. That's trivial. The next trivial thing is that if mod k equals 3, then no, you're really not interested in it either. Because then just after one step, it's going to be 1 or 5 anyway. And I can even skip the values 1 here, I think. But let's check that out, as in so if we get inside here, then we do a step, then it must be mod 6 must be equal to 1, otherwise we will not get inside here. And that means that the new L must always be smaller. Is that correct? Well, if I cannot remember, but I think that's the case. So I'm going to say next. L is next. So that holds in this case. Or not. Interesting. Okay, that's pretty quick. What's going on? Oh, only if it is still 1. So 7 goes to 11, which is larger. But this is of the form 5. Yeah, so what I wanted to say was that to the mod 6 of next equals 5, or next is less than L. Mod 6. So that works. Now we're going to test if this works for a reasonable amount of numbers. Let's see if we can do 10 million. Maybe I should not have printed it, but it seems to be doing pretty fast. Wait, this is level 1, 3 Dutches. Oh, 2, 3, already over 20 million. Thought I typed. But I'm convinced, you know. It's like, so sometimes you really see like a pretty long one here. Well, this is larger than this one, and this was, you know, it gets smaller, this is smaller, even smaller, and then it's form 5. Yes? In other words, if it does not become equal to 5, the mod 6 does not become equal to 5, it becomes smaller. Smaller, 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 smaller. So that's just one possibility. Either it becomes, mod 6 becomes equal to 5, or it becomes 1. Therefore, we can also skip the other one. So now we are only interested in the values where mod equals 5. Well, that means that we can just start at 5 and then skip with 6 at a time. Then you don't have to do this test anymore. But also, now I want to do a step. If I do a step, I want to continue doing steps until it is 5 again, because I'm not interested in intermediate values anymore. I'm not even going to print it anymore. Right, so run over all the values of k that are equal 5 modulo 6. And then we do a step. This is now a single step. No, that's nonsense. I need to begin with a step. So I do one Collatz step, and then while the modulo is not equal to 5, and also not equal to 1, then I continue doing steps until that is the case. And then we can print it. Now, it also does not make any sense anymore to print a mod 6 value, I think. I'm just going to do that here to be 100% sure that I did the loop correct here. It's kind of silly because, yeah, well, of course I did. Of course it is correct. But here, let's just suffice with printing a single next value for now. Is this 100 million? I think I did 100 million, right? I did 100 million. Okay, let's go back to 1000 for the moment. So yeah, it doesn't make any sense to print the modulo 6 value anymore because they're always 5. Now what I want to do is do this in a loop until okay, I want to keep track of this value here, of the n here. So maybe I should not loop over k, but I should loop over n. And then we begin with n equals 0. And we do simply plus plus n. And then k is actually just 6 times n plus 5. And now I do no longer want to print k, I want to print n. So here I have calculated L, but really I want to print the n here. So let's say we make a function that's called n or something like that. No, that's nonsense. Call it find n. It's a ridiculously simple function. It returns a number. So case of the form 6 times n plus 5. So if subtract 5 and then we divide that by 6 and then we have that value. Yep. No, can even add an assert that this is divisible by 6. Must be of that form, of course. So that does not hold when it is 1. Or maybe you should do that as a special case, as in continue. Well, I still need to print it or want to print it. Yeah, so I invented a new Collatz conjecture thing. Instead of Collatz numbers, now we have n. 0 goes to 1, 1 goes to 2, 2 goes to 0, 3 goes to 5, 4 goes to 1, and so on. Now, obviously, if this number is smaller than this number, now let's not take the 0, let's take this one. 12 goes to 4. Then we can stop because we already did 4. 4 went to 1, but it's before that. So I want to keep adding arrows here until I get a value that is before the 13, I guess. Oh, this is the n of L equals the find n of L. We print that here. And then I want to print again an arrow with the next number where we do convert L into L. So that must be a loop here. I don't know, some loop. Infinite loop. Yeah, we have an L, we find the next form of that. Yeah, this continue is not working anymore. No, fix that in a minute. Find the next L, we do that here. Print that, and then we continue with converting that L into the next one, and so on and so on, print that. However, if NL here is less than the original, no, sorry, if if NL is less than the original N, yeah, well, might as well do that then. So we print this until, let's do here, while, So we stop if NL, while NL is larger than N, correct? That's the original N. And that's not working because NL is not defined here. Let's put NL here. So I can assign it here and then test it here. And this just will have to be an else, I guess. Or does it? Wait, it can just break out of the loop. Why not? It should simply be a break. No need for that. Nope. First of all, I should not have printed a new line here. Nor there then, I guess. And something goes wrong. Two results in 2. Is that true? So 2 is N is 2, then we have 12 plus 5 is 17. No way that goes to 17, of course. Or we would have found our what is it? Counter example. What the hell is happening here? Okay, 17, and this is a single step, so 17 times 3 plus 1 is 35 divided by nothing, so just 35, I guess. Modulo 6 is 5. Yeah, so nothing is being done. Huh? What? Okay, I'm confused. Our computer is too fast. Okay, 0 goes to 1, 1 goes to 2, goes to 2, goes to 2, goes to 2. That's not even true. 2 goes to 0. I have to step through this. So I'm just worried that I cannot print the number values in the debugger, but let me try that to do that. Debugger. No, it you cannot print it. I'll just have to make it work for a non-number psi. So number is I don't know. Let's make it a long. No, I don't like that. Wait. That is not what I want. Let me just use here until Z set. And I can overload it on for long. And then I need to write and make odd. I have a feeling that is Z set as a pointer anyway. So there's not much difference between a reference and a pointer then, is there? If this works at all. But then again, there's a const reference here. Okay, it's, where's my make odd? Yeah, they work with reference and const reference, so I guess. Make odd just takes a reference. So maybe it should not pass by value then. They don't. I can hardly believe that its size is very big. Oops. Alt top. Yay, now I can print it. Okay, so we begin with value of 5, obviously. And that becomes, 5 becomes 1. 3 times 5, 15 plus 1 is 16, and then we have 1, so L is now 1. Well, that means that we do not do this because L is 1. And then because it is 1, we print it. And we break, and we go to the line even. 0 goes to 1. So we go to the next n, and the next k, which should be, well, 11, yes, 5 plus 6. 3 times 11 is 33, plus 1 is 34, divided by 2 is 17. So L equals 17. And 17 modulo 6 is immediately 5. Therefore, we do not enter this while loop. It is not 1. Now we find an L value of that. Well, that is 12 plus 5, so it's 2 times 6, so NL should be 2. Yeah. And we print that. And now the original n was n, so we became larger. Therefore we want to continue. So we go to the top again. And now L is 17. Yeah, we didn't do a step. Quit. Yes. So here I'm doing a step, but in the loop, I'm not starting with a step. I think that this step should be done inside the loop then. What? How is that possible? So the next same thing, I mean, 0 goes to 1. Okay, it's already going wrong. N is 1, K is 11, L is 17. Therefore we continue. And now 17 must become, 17 goes to, let's take a calculator. 17 times 3 plus 1 is divided by 2, and again divided by 2 is 13. Yeah, I understand what is going wrong. Let's step through it anyway. Oh, or not. So L is excuse me? Oh. Yeah. This must be a step on L. Okay, it's the original, and then I might as well, I'm not using K, I'm comparing with N later on. K is not used anymore after this. Yeah, we just use N. So hey, why not immediately define K here and then use K instead of L. Just rename K to L. L to K, I mean. So we have our K, do one step, and then while it is mod 6 is unequal 5, do more steps. If it is 1, print that and break out of the do while loop, then we get the next N. Otherwise, we find the end value of that K and print that. And then we continue while that is larger than the original N. Now this should work. Yes. So 2 goes to 0. We saw that before. So now we have 3 goes to 5, which is larger, goes to 8, which is larger, goes to 0, which is smaller, and therefore we stop. By the way, this one is unequal that one. I need to print something else here. I mean, if n equals 1, then we have actually 6 times 1 plus 5 is 11. So this one stands for 11, and that one is, you know, really the original one. So let's print 1 here instead of the n value 1. And now let's make this loop big again. Well, big, 1000. Okay. Pretty long versions here, but you do see that it gets smaller already from here to there. But yeah, I'm not sure what to do with that. It does get smaller, but does it prove anything? I don't think so. I think it's not a coincidence that this is power of 2 minus 1. But that aside, so let's look for 1000 and we won't have that. 255. Is that also long? Not really. This one is way longer. Way longer. I find this a very interesting sequence because it really becomes larger and 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 larger, and then finally it becomes bang small. This becomes larger a lot. Let's type these numbers into the integer number database. Is that cheating? Nah. Just curious. The online encyclopedia of integer sequences, I think. Yeah, it is. And then we're going to enter these numbers. Yeah. That doesn't really have to be changed into a comma everywhere. It appears, and it 255 is indeed the one that becomes before it. After it becomes 511. That's interesting, because that's not the case. That is not the case here. We get 28 as the next number. It can hardly be a coincidence that this appears like that. That is the only entry. Triangle read by rows. TNM is 3 to the power. What? 3 to the power m times 2 to the power n minus m minus 1. The number of neighbors in an n-dimensional cubic array. Beats me. Ah. Ah. TNM, blah, blah, blah. First part of the Collatz sequence for the number 2 to the power n minus 1. So Collatz is even mentioned here. I have so no clue what this is about. Does anyone see this? That's equals 17 because a cell on the face of a 3D cube has 17 neighbors. Okay, someone explain that. Yep, I have no idea what I mean. Where are the computer scientist students when you need them? Anyway, I don't think it's related. Well, it's funny that they mentioned the Collatz conjecture. But hey, they also mentioned 2 to the power n minus 1. So now I want to see what the 511 returns us. So that would be as long as it grows, grow. So these numbers, It should also appear here. Methinks. Well, this is just it's just a repeat of triangle things, right? So this is basically the new next line. Oh, that there it is. 511 767 1151. Yeah, this is just the next bunch here. So then this sequence here is what we get at 127. $191, 287, etc. Okay. Well, if they know that, then why wouldn't they know this one, right? Let's try to find that one. Or is that beyond the knowledge of the online integer sequence database? Sorry, but the terms do not match anything in the table. Oh well. My idea, because you have to go one step further, my idea is that the numbers are telling us something if you write them in binary. So I want to print them out in binary. That's never easy, is it, to print numbers in binary? Why on earth can we not do that easily? I was going all the numbers. I was going to make all the numbers cons references. binary wrapper. Yeah, it's never 0. Yeah, and then the inverse of that. Yeah, Post Bunny. Sounds like a good story. What am I doing wrong here? Bit is 1, while bit is less than k, then definitely we want to increase it. What if it is equal to k? then I guess I do not want to increase it. But then sometimes, as it's equal, I have to increase it as well, and then it becomes larger than, oops, it definitely becomes larger than k. So then I can start with shifting it back. Or just do that here. And then larger than 0, I don't think that makes any sense. It must be larger than 1 now. Because I'm gonna shift it back. And still. What if we don't do this at all? Well, k is never 0, so minimum is 1. So less than or equal 1 equals less than, yeah, so bit is 2, shift back 1, okay. What is this? Oh, stream in binary does not exist, it says. What then have I been writing a second ago? Oh, an operator without anything. Without anything at all. Boing, ping. Right, let's go to the top-ish. So, what do we have? Interesting. It goes to something that ends on 1010101, which then ends in a power of 2, which then gets greatly reduced, but not at once. So this one goes at once to 1. Well, it's not really 1. This is 11. But anyway, it goes really far down here. This one goes far down, but not entirely. And here you have one with a lot of zeros, and then just 2 zeros are removed. What? So that it's the ones with a lot of ones. If you have 1 1 single 0 1 1 1 1, you get something that's pretty long. Here also there's a single 0. It's reasonably long, not as long as that one though. Here we have only ones. I don't know why is this one longer. Ooh, this one is long. That one is really long. 1 0 1 0 4 ones. So another that is really long. Like really, really long. Here, this one. Pretty damn long. No. That looks random to me. Well, one thing I had already thought of, namely if it ends on 2 zeros, then the next one is smaller. So every time it ends on 2 zeros here, it's just one arrow. So you gotta wonder if you can turn that around. No, it's like this. You only get a single arrow because, well, 0 0 gives a single arrow. Now if I grab for an arrow, we get everything of course, but if I grab for an arrow, 2 arrows I mean, and then a minus V, so now you get only the ones that are a single arrow, and not all of them end in 0 0. Sometimes they end in 1 0. So yeah. In fact, it is just 1 0 0 0 0 0 1 0 0 0 0 0 1 0. So there's definitely a good reason for it. Definitely good reason. So we'll be able to see that reason at the beginning. Even here, you know. 2 that ends on 2 zeros, and then we get one that ends on 1 0 again. And then 0 0 0 0 1 0. Why? And what happens with the stuff that is a void? Yeah. So every time this is of the form where you get every possible bit pattern. Get every possible bit pattern with 2 zeros. But some bit patterns also get 1 0. So what is so special about this on this value? AKA 0, 2, 4, 6, 8. Well, I would say all the even numbers. Yep. Well, all even numbers mean that this is a 0. So it ends on either 3 zeros or 0 1 0 or on 1 0 0. That's the 3 possibilities then. So if I would get the first, well, just the last 3 digits of the first thing. That's only 0 0 0 1 or that. Oh, it can only end on these 3 trailing ones. In other words, if it is of the form 8 times n plus 0 or 2 or 4, then it gets smaller the first step. Yeah, I'm not even sure if that makes... well, you can use it in the sense that if there is a counterexample, and then that counterexample is part of a loop, or it's part of a series that never goes to 1, and therefore it has to go to infinity if it's not a loop. And of that whole set, then there is a smallest number, and that smallest number then may not be of this form, because if it is, it would become smaller. But then you would have to prove that for all the other forms, it also gets smaller. Smaller than the original, but not in the first step, but later on. The others being plus 1, 3, 5, 6 or 7. Yeah, well, why not? The 1. Oh, this one ends on 0, 0, 1, and it goes to one that is smaller, but not very quickly. So what happens here? It's not necessarily a trivial case. Let's try the 5. The 5 is a trivial case. I think that's provable, probably. It goes to a smaller value in 2 steps. So yeah, that's definitely. I'm convinced I can prove that. So 5 can be skipped out. Which others do we have? 5. Okay, so what about 6? The 1 was not trivial. Let's try the 3. Not really trivial, I guess. And the 6. That doesn't really look trivial. Now we have 7. Also not trivial. Okay, I think I'm done for today with the Collatz again. I just couldn't do this in my head, clearly. So I was just really wondering if there was not a more obvious pattern here. Like, let me type it out. Now I know that it is a dead end anyway. It can be less secretive, I guess. So I thought if you have a number like you have a numbers like 6n plus 5, right? When for every other form it is already proven then, or it Collatz conjecture holds if it holds for these numbers. Now this is obviously odd, so that goes to times 3, it's 18n, plus 15, plus 1, so that becomes then 16, oops. And then it's even, so we have to divide this by 2, so this becomes 8n, 9n plus 8. And now you don't know if it is odd or even. If this is odd, then we already did grow. You also don't know if it is of this form or not. So that depends on the n. I mean, if the n, I mean, I thought it would like depend on the last two bits of n. So in other words, how often n can be divided by 2. What the modular of 2 then, if you divide it by 2? Because you can write n in two forms. Yeah, it's either 2m or it is 2m plus 1. So in this case, this thing here equals 9 times n is 9 times 2m is 18m plus 8. Yeah, which then we have to divide by 2, and then it becomes 9m plus 4. And this one becomes 18m plus 9 times 1 is 9 plus 8, 17. Which is definitely odd, and coincidentally can be written as 6 times 3m plus 2. 6 times 2 is 12, so plus 5. So if this n is odd, then after a single step we have again this form. So mod 6 is again 5. But it's also larger because 3m is larger than n already, and then plus 2. So okay, it did grow, but at least we have again something of this same form. Well, in this case, we're not done yet, because now it depends on whether m is even or not. Yeah, so if you write n in binary form, then this is the last bit. And then if m is even or not, this is the second bit of n, and so on. So I thought if you write n as a binary, then you can see all those bits, and then maybe I can see a pattern. And it turns out that there is a certain pattern for the first 3 bits. First 3 bits is already enough to see if in certain cases that it will and become smaller than the original. I had hopes that like it would only grow forever if it ended on 11111 or something like that, but that doesn't seem to be the case. Okay, so to continue this, we can say M is 2 K L M N. I don't know. So, well, why not L? Or 2L plus 1. And in this case, 2M plus 4 then equals 9 times 2 is 18M plus 4. Divided by 2. Sorry, that's an L. Is 9L plus 2. And in this case, we got I get 9 more than what is above here. 9 times 1, so 9 plus 4, 30. Which is 6 times 3L plus 2 plus 1. So that's not of the 4 plus 5. So we still have to continue this one as well then. Sure. Okay, yeah, I'm gonna call it quits. It's just shit, Jeff. The forever, the forever out of reach solution. I'm gonna stop streaming too. I don't want to attack my current Vulkan engine problem yet. Going to do something else. So good night in advance.